programming. And so a lot of kids, they'll leave that.
Okay, folks,
Yeah.
welcome to Linear Algebra. Let me start off by, let's let me hit the high points on the syllabus. Okay, so my name is Jim. Something. Anyway, so you can use that part of my name. My office is on call 205, which is just across the quad. My office hours this semester will be from 7 to 8 a.m. Well, not exactly 8. I've got to leave a little early for my 8 o'clock class. And whenever I get back to this class until 2, say what you will about me. I'm pretty generous with my time. So if you're struggling with this, come by and see me. I'm happy to help you out. We didn't keep everyone use this. Does anybody use a landline anymore? Whatever. And that's my email. I'm usually fairly quick about getting back to you, but it's gonna be a holler if there's any trouble. We see something about the class. Also have a web page. The URL is on the syllabus, which the syllabus is posted on Canvas. It'll also be posted on my web page. I am going to record this class. We'll record it every day that I remember, which won't be every day. And also Zoom synchronously. Don't do it unless you've got the plague. You should probably come and show up, but that option is available if you can't. Your best experience will be being here. Some people ask about taking notes, take notes, but I would pay attention in class and talk to me. Any questions you have, better, because I post the thing up on Canvas after it's over, and it's also on my YouTube page. So if you miss something, you always go back and look. So that kind of eliminates you really having the pressure of having to take notes. Also, I taught this course a number of times. If you look on my web page, my Clemson web page, not on Canvas, you will find every quiz, every exam that I have given in this class. So that's a resource for you as well. Does everybody have a book? This thing? No? If you have a book that says Linear Algebra on it and it doesn't say it's for total limits or something like that, it'll probably be fine, because whatever I do will be in there somewhere, right? You might have to bounce around a little bit. So the structure of the class, as far as what I'm going to do, as far as grades go, is let's kind of go through this. So here's what's going to happen. You have 3 exams, and I have tentatively set the dates at September 27th, October 27th, and November 20th for 3 exams. They will be 10% apiece. The final will be 20. And the other, I call it homework average. It's really more like a quiz average, will be worth 50%. So that's going to be the big chunk of your grade is your homework quizzes. I am not taking up formal homework usually. I reserve the right to assign it, but I will probably make it up myself. I don't use these online things. What's going to happen to you all is I am probably going to give you 2 quizzes a week. You should count on 2 quizzes a week, right? I reserve the right more or less, but I'm pretty regular. Probably be a couple of. I'll have one due on Tuesday, probably one due on Friday. Not this Friday. I'll start that up on Tuesday. So there's instructions on Canvas about how to take a quiz. Read them because the Canvas people still haven't done this right. There will be two things posted for your quiz. There's a little rocket ship logo. You go on that, and that's your quiz. You take a piece of paper and take it. When you're done with that, you make a PDF and you upload the quiz, and then you upload it to the assignment version of the quiz. So it'll be two things to say quiz one. It won't be a rocket ship, won't be paper or pencil or something. That's the assignment. You uploading it to the quiz card is the timestamp that you finished it, because these will all be take home. The quiz will all be at home with some specified time on it, between 1 and 2 hours probably. You upload it there, and that shows that you finished it on time, and then you upload it to the quiz part or the assignment part, and that's so that the grader can grade it, and we can look at it later if you're confused about why you missed something or something like that. That's going to be worth half your grade, those quizzes that you take. And I'm going to suck it to you. I'm going to make them tough. And I told the grader to grade it tough. Not because I need, but because I love. Because I'm going to curve those homework or those quizzes, right? So it will be around at least an 80. So don't worry if you've got 45% on this quiz. If you're above average, that's above an 80, right? At any point in the semester, I can give you a real-time update on where you are. Do not trust what's on Canvas. Canvas also can't add numbers. So, but at any point in the semester, I will tell you exactly what your score is and exactly where you are. You can come talk to me every day. I don't care, right? But anyway, I am going to rock and roll you on quizzes. So expect them to be hard. They aren't hard to be super hard, but you would expect them to be challenging, because I'm going to curve it around a generous mean, and I want to prepare you for the exams. I would rather you have the wailing and the gnashing of the teeth when you're taking the quizzes, and then take the exam and say, oh, this is much easier than the other way around. So the best thing for you to do is kind of stay on top of things. When you miss something on the quizzes, make sure that you know how to do it. Come tell me or come ask me if I can be of any help. The attendance policy is this. You all are all adults. You know, if you don't show up to class one day, I totally get it, but it's a bad idea. You should be here. I will tell you this, because Clemson's got a new policy. If you haven't done any quizzes or something by whatever it is the ad day, I have to drop you. So do your quizzes stuff, because if you haven't done it, you're going to kind of get booted out of here. And that's Clemson's policy or whatever. But come to class, and that will cover a multitude of sins. Now, if you have to miss class, that's okay. Just come. I'll, look at the recordings of class and try to make sense out of it. If you can't, that's what I'm. Okay. Any questions on the implementation of class or anything like that? Yes, sir.
So are you using my lab for the homeworks, or is it all like your own stuff?
As far as the homework goes, some people make the mistake of thinking I have no homework. There's homework. There are problems at the end of every section. You should do those. But those are to prepare you for the quiz, right? If I give you something, if I want you to turn in a homework, which actually the past couple of semesters hadn't happened, I will post it on Canvas and tell you it's there, right? I want you to turn such and such in.
So don't buy my lab.
Especially if you have to buy something, you don't need to do any of that stuff. Yeah, so the way you're being assessed is you should be doing homework every day. You should go home after this, work through the problems, come see me, or whatever if you're having difficulty with it. But as far as what you're grading on, it will be the quizzes. That's what's checking on the homework stuff. That's your question.
Yeah.
Okay, others. Okay. So let's talk some linear algebra. So what is this all about? Well, first I'm going to tell you what a linear equation is. A linear equation is an equation of the form there, the xi's are variables. And the AIs and B coefficients. Call it coefficients equation. Are in either the real numbers or complex numbers. We're going to focus mostly on the real numbers. We'll talk a little bit about this later. And actually, it could be in any field, the rational numbers. That and B is R. So, for example, you've seen these all the time. Here's an example of linear equation. What does that look like to you? Right, this is an old friend. This is a line, right? And so maybe I've got this little rearranged a little bit. So here, my x1 is x, and my a1 is negative m, my x2 is y, and my a2 is 1. There's my b. This is actually a line, and this is where the linear equation sort of thing comes from. A linear equation with two variables. And actually, this makes a line in the plane, right? That's one of the first things you probably did when you first did an algebra class, is start tracking lines. Here's another one. Now I've got three variables, x, y, and z. So those of you that said that you're in Cal 3, you're going to be encountering this. Anybody want to guess what this would look like? So the line, I graph it in the plane on a piece of paper. This I would have to graph in all of space because there's three coordinates, if you will, an x, y, and z. Anybody want to guess what this looks like if I were to draw all points in three-dimensional space that satisfy that equation? Is it not plain to you? It is plain, right? It is the analog of a line. So imagine a line in the plane. Now you're stretching the plane out into space. You take that line and spread it out, and it becomes kind of a sheet, right? And that's essentially what happens. There's a linear equation, right? Yeah, I think you'd have to like an amphibian or something to understand what this one looks like, because it's four-dimensional space. We can't really graph it, right? Because we're used to living in three-dimensional space. However, it certainly has points on it. I can tell you one point that's on it. Can anybody give me a point that's on this? Yes.
1, 0, 0, 0.
Oh, I like that. That is a clever way to do it. Okay. Can you give me one more? Do your same thread. 0, 0, 0, and there you go. And just by playing this game, I can get a lot of points, right? There's a lot of points on this. So I know that I've got at least two solutions to this. More generally, these are just single linear equations. I have a line, I have a plane, I have something crazy, right? And by the way, how many of you are engineers? So you might think, well, why would you care about linear algebra beyond three variables, Jim? Because after all, we live in a three-dimensional universe. Well, depends on what physicists you talk to, but three dimensions are all that I kind of really can understand myself. However, for example, if you do mechanical engineering If you look at the degrees of freedom of, say, a hydraulic robot arm, if you need two arms, it requires more dimensions in the space because you've got several things moving around, right? In fact, I remember seeing equations for robot arm movements that required 6 parameters to describe things, right? So even though we're not used to walking around in 4-dimensional space, it's very useful. There are places where it does show up in problems. More generally, a system of linear equations is a collection of one or more. So here's a couple of examples. Here's a couple of systems. Take x1 plus x2, 1. x2 plus x3, 1. x1 plus x3. This is a system of linear equations. Now, this equation has influenced many solutions. Just the first one by itself. Everybody agree with that? Because it's a line, right? How many points are there on the line? Equally many. Everybody good with that? Same for the second equation. Equally many solutions. Same for the third. But how many solutions work for all 3 equations? This is a big theme of linear algebra. And I'm doing this on the first day. We're going to look at systems of equations, but this thing will come up over and over and over again throughout this course. In fact, it's essential, it's kind of lifeblood of linear algebra. So here are some big questions. Given a system of linear equations, here are specific questions. Question 1. Is there a solution at all? Well, for example, if we look at a single line, it's got influence, right? But what if we have 2 lines? Right? So what if we have infinitely many solutions, infinitely many solutions put together? How many solutions are there? There's 0. Why are there 0?
They don't from the same line.
That's right. That's right. So I can modify this one a little bit just to make my life easier by dividing by 2. That's one of the things that you can always do with linear equations is you can multiply by any non-zero element, right? And you get the same solutions, right? X plus y equals 1, x plus y equals 2.5. Oops. Right? I mean, this is on the face of it kind of ridiculous, right? How can x plus y equal this? These 2 equations apply to 1 equals 5 halves, which is true and false, right? What's actually happening here geometrically? Well, this is y equals 1 minus x. So this first one looks something like this. And the second one is y is equal to 5 halves minus x. So it's got the same slope as the first line, but it's got a higher y-intercept. So these are two parallel lines. It's probably not a very good scale, but no solution, right? Okay, let's think about linear equations here. Does it have a solution? Another way to put this is system consistent? This is a vocabulary word. Consistent means, when I say a system is consistent, that means it's got at least one solution, maybe more than one. The second question is, how many solutions? How many solutions are there? And three, what are the solutions? Now, let me give an example we can build up from. Actually, let me do something numerical. C and dx plus dy. Look at these two systems, like variables are x, y, and the other beginning of alphabet letters are just numbers, right? I didn't specify. How many, and just for ease, I guess, we'll assume that A, B, D, B. We don't have to worry about zero and spheres and like that. Let me ask you this. What are the possibilities for solutions? How many solutions can you have in this system? What are all the possibilities? Yes.
Well, there's two lines, so they could not cross, and there could be zero.
Okay.
They could intersect at a point, or they could be directly on top of each other and have.
Everybody see what he says? The two lines may be parallel, but not the same. They don't meet. We saw that in the previous example. If they're not parallel, how many solutions are there? They've got different slopes. They can only hit one point. Right? And the last one, I'm glad you got this one too, is the other parallel possibility is if the two lines are the same, right? And that means you've only got one line, which has infinitely many solutions, right? So it looks like if I have a system of two linear equations in two variables, I have 0, 1, or infinitely many solutions. You know what's the first cool thing that I'll tell you in this class? It doesn't matter. Any system of linear equations in any number of variables, that's it. You either have 0 solutions, none at all, it's inconsistent. You have only one solution, you have a unique solution, or you have infinitely many. Every linear algebra problem, every linear algebra system has this. This is in fact always true. For any system of equations and any number of variables, those are the only three possibilities. So I'm going to write this down to sort of get that out there. There. Given any solution, or I'm sorry, any system of linear equations I'll call the system S, so you can let that system one play it. Exactly one of the following is true. One, S has no solutions. None whatsoever. Two, S has a unique solution. So it's got one and only one. Three, S has equal and many solutions. So, as an upshot, if you remember this example we had earlier, see if I remember. I believe you gave a solution 1, 0, 0, 0, and we gave another solution 0, 0, 0. This system, actually, there's only one. This system has two solutions, correct? That means it has to have infinitely many, right? I don't even have to check anymore. Once I know it's got two different ones, there have to be infinitely many, right? That's kind of a cool thing, right? I mean, that tells you a lot. I don't have to check 100,000 things. I'm done. Okay. Now, let's get busy trying to solve some of these things. I gave you a system just a bit ago. It's 3, 1, X2. Okay. Let's be completely ambitious and try to find all the solutions. I mean, if we could do that, that would tell us our answer. And of course, I hope it does have a solution and not. How would you solve this? Yeah.
But if I could ask a unique solution is if they're all 1/2, that's a solution.
Okay, so you figured out the solution, right? And what is it?
They're all 1/2.
Okay. And how did you do that?
But it's a two variable, they have two other multipliers, and there's one on the other side, you just split the one.
So you do a little substitution and make some observations. I mean, right, one thing you can do is you can subtract, say, this equation from this equation. How many of y'all have done this, like maybe in high school? So, you probably did this with two variables and two unknowns, and you subtract things or whatever. So if you subtract these equations, you get x1 plus x2, see x1 minus x1 is 0, x2 minus x3. Everybody agree with that? And that gives me a piece of the puzzle, right? Because what it says is x2 and x3 must be the same, which is jiving with what you said it should be. Right? And now that I have x2 and x3 are the same, I can kind of dump this knowledge into this equation here. And let's see, x2 and x3 are the same, so this is 2x2 equals 1, so I get x2 is 1/2. But I know that x2 is x3. So now I have x2 and x3 are 1/2. And once I've got that, I can deduce that x1. And your solution is correct. Everybody okay with that? Easy peasy lemon squeezy, right? The problem is these equations are very symmetric. It wasn't too difficult. I mean, you did it in your head, right? It wasn't too bad. This is not very systematic. If I gave you 4 equations and 7 unknowns, it's a little bit more frustrating. So I'm going to give you something. I'm going to do the same problem. I know this is an easy problem, but I think it's good to take the step here. I'm going to do this problem again by writing this in a matrix. So let me write out the equations a little bit more dramatically here. X1 plus X3, 1, and X2 Everybody? Now, one good thing to do, we play around with linear algebra here, is to write this in the form of what we call an augmented matrix, right? How many variables do I have? I've got 3 variables, right? X1, X2. So I'm going to need 3 columns here, 1, 3, each. So X1 plus X2, 1X1 plus 1X2 plus 0X3 is equal to. Right? Let's look at the second one. 1X1 plus 0X2 plus 1X3 is equal to 1. Right, okay. 0X1 plus 1X2 plus 1X3 is equal. So notice that instead of writing X1, X2 all over the place, this is a much more compact and streamlined way of writing our system. Right? You can just read this like X1 plus X2 is 1 and so. Right, okay. Now, how do we get down to brass tacks? Right. Well, what we have to do is we have to do some row operations on this. And what row operations are is there's a way, it's the way that we're going to operate on this matrix so that it doesn't change the solution set, right? Because I want to turn this, I mean, these aren't the world's most complicated equations, but it would be super groovy if I could turn these into easier equations, right? I want to turn these potentially complicated equations into easier ones without ever changing what the solutions are. So I've got to be careful about this. Row operations are what allow you to do this. And I'll make a comparison to something that you've probably seen before. We're allowed to do one, swap any 2 rows. We're also allowed to multiply any row by any non-zero number. Number 3, you're allowed to add a multiple of any row to a different row. These row operations do not change your solution set. And let me kind of at least give you sort of a feeling for why that's true. Right? So if I'm solving these equations here, the first thing I can do is swap into 2 rows. It doesn't matter if I write this equation first and this equation first, it's the same substitution, right? That's kind of nice. Does everybody agree with that? The solutions to this equation are not changed if I multiply it by, say, 2, right? Or -1, right? It's still the same line if I multiply the whole equation by 2 or -1. Everybody agree with that? That covers this one right here. By the way, I don't want to multiply this equation by 0 because then I get the equation 0 equals 0, and that equation has everything as a solution, right? Because it's already true. You can add a multiple of any row to another. And this is probably the way that you've done these kind of problems in the past, right? You can take, for example, -3 times s, which doesn't change solutions, and add it down here to get rid of the 3x, right? And this is just us stating what you're probably used to in matrix. Right? So let's go through this thing right here and apply some row operations. 1, 1, 0, 1. I put that line here to signify that this is what's on the other side of the equal sign. So one of the things that I can do is I want to be systematic about this. I want to make this, I want to get rid of, I want to turn as much stuff into zeros as possible. So I'm going to do the following row operations. I'm going to leave the top alone. I'm going to multiply top row by -1 and add it to the middle row. Right? So that's going to be 0. That's going to be -1. That's going to be 1. And that's going to be 0. Everybody okay with that? And I'm going to leave the bottom row alone. Now, I'm going to do one more, let's see. Get that. That should be a 1. Let's have a watch around there. I didn't do it. In the bottom row. The next step is going to be do one more step before I take this apart again. I am now going to take the second row and just straight up add it to the bottom. So I'm going to leave the second row alone. And I'm going to straight up just add this to the bottom. That's going to give me a 0, 0, 2, and 1. Notice how this matrix here, down the diagonal, I have numbers, but I have zeros below the diagonal. This is called a triangular matrix. This part that's to the left of the dividing line here. And this gives me the following equations. This gives me minus x3. Everybody agree with my interpretation of these equations here? This allows me to do something called back substitution. I've got 3 equations, so you might think the parts of Jimmy didn't do anything, but there's one of those equations that's easy to solve. Which one is it? The bottom one. And the bottom one gives me, and this is why it's called back substitution, the bottom one gives me x3 is 1/2. But now I know that, I can put that back into here. And it's a 1 step. Minus x2 minus 1/2 is equal to 0. And this gives me that plus, thank you. That gives me x2 is 1/2. And finally, I have x1 plus x2 is equal to 1, but I know what x2 is. And this gives me x1. And there's the solution. Now, you were quicker on that first problem, right? But it can get more complicated than that. So let's try this, shall we? Up this one right here, x1 plus x2 plus x3 plus x4 is 5. X1 plus 2x2 plus 3x3 plus 4x4 is equal to 15. X1 plus 2x2 plus 4x3 plus 3x4 is equal to 13. And x1 minus x3 minus x4 is -2. This one is, there are some symmetries here, look carefully, but this one is not quite as clear, is it? Right? I mean, nobody wants to go through and try to solve one, right? So let's see if the matrices help us. First thing I need to do is reimagine this in a matrix form here. So 1, 1, 1, 1, 5. So that's x1 plus x2 plus x3 plus x5. Right? 1, 2, 3, 4, 15. Well, okay with that. Is everybody clear on where I'm getting my number? Right? Okay. 1, 2, 4, 3. 13, I guess. And here, I've got the next one here. 1, 0, -1, -1 equal minus. Okay. Everyone know piece of Okay, I'm going to systematically go through this thing again. First thing I want to do is I want to start over here and just eliminate down, right? So I'm going to do several at once. I'm going to leave the top alone. And then going down to the next. Going down to the next level. Multiplies by -1 and add it here. 1, 2, 3. Everybody agree with me? You should probably check me on that. 1, 2, 3. Multiply by -1 added here. I get 0, 1, 3, 2, 8. Right? Multiply by -1 added down here. I get 0, -1, -2, -2, -7. Right? Focus. Yes.
Would you like skip, like hypothetically, would you just skip like doing subtracting from the first one and just subtracting the second one? For the third?
So what, you want to use a different row?
I was just wondering, because like for the second row, you're subtracting from the first row. If you're on your third row, could you subtract from
Think of it this way. What I did every time is I multiply top row by -1 and add this. Times -1 and add this. Times -1 and add this.
Okay, yeah, but could I use the second matrix, like the second row for my third row? Like, could I multiply it by -1 and add it to this for the second?
So yes, I think I'm answering, but we're gonna move on and do that.
Okay, yeah.
Right. That's exactly, because we've got it better, but it's still a mess, right? So let's now key on this and use kill the ones below it, right? So I'm gonna leave the top row alone. 1, 1, 1, 1, 5, 0, 1, 2, 3, 10. Now I'm gonna multiply this by -1 times this one, and I'm gonna get 1 -1 -2. Okay, so far. Times and actually just times +1 and add it to this, right? So just straight up add. 0, 0. Oh, I got total luck now. Right, didn't I? Because that's 0, 0, 1, and 3. Everybody okay with that? Old Jim's living's like right. So this actually allows me to back substitute, right, and get. In fact, it would be a unique solution. Let me rewrite these equations real quickly. X1 plus X2 plus X3 plus X4 is equal to 5. X2 plus X3, 2X3 plus 3X4 is equal to 10. X3 minus X4 is equal to 2. And my favorite equation, X4 is 3. Yay. So I've got that one. And now I just work my way back. I know what X4 is. It's 3. Now I use that here. And that gives me, if that's -3, the next 3 is 1. And now I use both of these pieces of knowledge. Get X2. Let's see, I get 2X3, so that's 2. And 3X4 is 9. It's equal to 10. So I get X2 is -1. Everybody okay with that? And finally, I have this right here with all my information. X1 plus X2 is -1. X3 is 1, and X4 is 3. So I get X1 is 2. So there's only one solution. X1 has to be 2, X2 is -1, X3 is 1, and X4 must be 3. Okay, any questions on that? I would encourage you to go through the homework at the end of section 1.1. Make up some, see if you can do this. Because the more polished you are working this, the smoother things will be. Any questions? Okay, well, we'll see you guys on Friday.